Hello everyone. So here's a box, right? And it's on the floor, and there is some friction, or there can be friction between the box and the floor. There isn't any now, but there would be, right? What would I have to do to have it move at a constant velocity? Well, of course, I would have to apply some sort of force to it. But how much of a force? Well, if I wanted it to move at constant velocity, the forces would need to be balanced, and therefore I'd have to apply an applied force just as big as the force of kinetic friction, and then it would move constantly. It would be in balance, if you will. Right? Move with a constant velocity. Well, that's linear motion, right? Let's kind of apply that a bit to rotational motion. So here's a device that you're going to see back in the lab. Okay, up here, it's got this little brass bar that sticks out. It's a very low friction rotational mount, so this thing can spin around really nicely. Okay, very low friction. And you can hang masses from different points down here. This is called an equal arm balance for reasons which, as you'll see in a moment, right, it's going to help us see this. So, what happens if I put a force on this object? What happens if I hang some masses at one of these points out here? Yeah, it rotates, right? It makes it turn, if you will. So I'm going to call that turning effect. This is different than force, which is a linear thing, right? This is turning effect. Now, there is a more technical name for it, but right now I want to be descriptive, okay, for the next day here. I want to be descriptive so that we understand what we're talking about. Okay, this is turning effect. Now, I could put some weight over here and put everything into balance again, and we can tell it's in balance because it's perfectly horizontal. And if it's not horizontal, it's not in balance. Okay? But is the amount of force that we're putting on each spot, is that the only thing which determines the turning effect, or even whether it turns or not, or whether it's balanced or not? What if I took this one and moved it here? Whoop. Now it's not in balance anymore. So it appears that in terms of turning effect, there's more going on than just how much force you apply. Now, if I apply a different amount of force here, I could get this to go back in balance. But notice, now the amount of weight is different. So it appears that not only the amount of force, but also where that force is applied, right, is going to affect how much turning effect we have. Okay? So the turning effect will depend on an amount of force and where that force is applied. And we generally measure where that force is applied with respect to the axis of rotation, which technically is up here. All right? So how far away it is from that. Now the question is, kind of how does this all work, right? So, think about this now like a door, all right? Just as an example of why we need to think about force and distance, okay? Hinges of a door are usually right along one side. Well, where do you generally put a handle on a door? It's almost all the way out here, right? It's always out on the edge. Unless it's some weird decorative door, right? And it's always out here on the edge. Why? Because that makes more turning effect. Right? It makes it easier to open the door, to swing the door. Try this sometime. Like, try our door, which is a big, heavy fire door, all right, going in and out of our class. Try pushing on it over here instead of where the door handle is, instead of the outside of the door. And you will see just how much harder it is to open the door when you push here than if you push just as hard out there. Okay? So it does affect how much turning effect you get, right, where you apply that force. So let's talk, go back to this balanced situation here and talk some terminology. Okay? So first off, the force we're applying with this device happens to be, of course, a force of gravity. And we could calculate that force of gravity by taking the mass we hang times the gravitational field strength, our old friend near the surface of the Earth, 9.8 newtons per kilogram. Right? I'm going to call this F1. Okay? Now, if we extend F1 up, this has a fancy name. It's called the line of action. This is the line along which the force acts. Okay? Now, why do we want that? Because then we can draw this. Okay, this distance. This is the distance from the axis of rotation to the line of action of the force when they are perpendicular to one another. So notice how I called this R, which is a distance, right? 1, because it's with F1. Perpendicular. I'm really using the perpendicular sign there. Okay? This is known as a lever arm. Right? It's a lever arm, R perpendicular, if you will. The perpendicular distance between the axis of rotation and the line of action. Now, don't ask me why, but there are some places in the world and some professors who might call this a moment arm. Lever arm is a little more common here in the US. Moment arm might be a little more common in Europe or England. On an AP test, it's also more common with older profs. So depending on who writes the test, they may talk about a lever arm. They could talk about a moment arm. But either way, it's this perpendicular distance. Now, we have a second one of these, right? There's a force of gravity, which is m2 times the gravitational field strength. And notice I made it bigger because, after all, there's more mass here. Well, we can draw a line of action there. And a lever arm for that one, R2 perpendicular. Now, we want to be able to measure these things in lab, right? We can calculate these forces of gravity as long as we know the mass. So how are we going to measure these? I mean, these would be a little hard to take a ruler, right, and put it out here and measure this and get the right line of action. But look at the way they made the device. It's very clever. Watch this. Isn't that the same distances? See how there's one right below the axis of rotation? So if we want the perpendicular distance, we can really just measure from hook to hook, if you will, right? From these little areas where we can hook these. There's only 3 of them on each side, right? And 1 in the middle. Okay? So that's how we can measure these, all right? Device is kind of made that way. It's kind of nice, so we don't have to use any trig or anything yet, okay, when we do this lab. This is called a clockwise turning effect. Why? Because as you saw earlier, if it was the only one, it would make it rotate clockwise. That means this one's called a counterclockwise turning effect. Because if it was the only one, it would try to make it rotate counterclockwise. So clockwise and counterclockwise, again, the 2 directions in rotation. That's how we distinguish these. Now, something here is in balance. Right? These turning effects, clockwise and counterclockwise, are in balance. We know they're in balance because our equal balance arm is beautifully perpendicular. Or sorry, beautifully horizontal. Right? So the question then becomes, well, what's the relationship? How does it work? How do you calculate a turning effect if you know the lever arm and you know the force? What combination of force and lever arm works here? So what I'm going to have you do now in the lab is you've got one of these set up in the back. You've got a bunch of masses. Right? You've got 2 brass mass hangers, which, by the way, be careful. They each have a mass of 50 grams, which is a significant amount of mass because they're made from brass, which is 0.050 kilograms if we convert. So you have to count those. You have to include those in how much mass is hanging here versus here. And the purpose of this lab is we're going to figure out a math model that represents turning effect, some combination of force and lever arm. Right? You'll know it's right when the numbers put everything in balance, when there's just as the same amount of counterclockwise turning effect as there is clockwise turning effect. Okay? And you should be able to figure this out after you do a few of these, right? So I want you to put these on there. Now, I only gave you a certain amount of mass because I don't want these to break, so they only take about 1 kilogram. So I only gave you certain masses. So it may be possible that you could, like, hang this one from a particular point with a particular mass, and you won't be able to balance it out over here perfectly. Might be close, but if it's not perfectly horizontal, it's not balanced. If that happens to you, don't use that one. Right? There are plenty of other combinations you can do. Please don't borrow masses from somebody else, all right, because I don't want you to break these things. Okay? They are just plastic with a very low friction swivel mount on top that I want to protect. Okay, so only use the masses on your table and the 2 mass hangers. Okay, so you'll notice on your page I want you to do enough to fill in your table, at which point you ought to be able to figure out what you need to do to calculate your turning effect to put everything in balance.